nice to meet you to the Python Barcelona event. I'll be starting. Thank you for the Jordi, who's actually not right now here, for the invitation. My name is Dorobek, and today I'm gonna tell you about the just chords and neural networks. I will start with a question. How many out of you know music out more from the theoretical point of view? So who of you is a musician? Who plays? Great. There are some of you. And how much people knows something about neural networks, about machine learning? Way more. Okay, great. Today I will explain you how to use neural networks to generate just chords. Why this crazy idea? Who at all would use machine learning to predict chords? And what actually is predicting chords? Imagine a situation that you're a composer, you're writing a song, and song consists of a melody, chords, rhythm, a lot of stuff. And you have a place when you have a melody, you have chords, and you don't know what to use. What kind of chords to use? I have this problem very often. I have really simple ideas, or I have no ideas at all. And I wanted to create a software that helps me to decide what kind of chord I can use. I'm a jazzman. I compose a lot, and I have these problems many times. And I came up with idea how I can use machine learning to solve this problem. Okay, so let's start with the basics. What is chord? What actually harmonic is? Do you know how songs, the basics of the song is? You have a chords, a guitar, a piano can play it. You have a melody, basically a vocalist, or some solo instrument like saxophone. You have a rhythm with the drummer. And the chord progression is a thing that shows how the song's basic structure is constructed. So chords tell pianist what kind of accompaniment he can play. And chord itself is a structure of at least 3 notes. If you play them simultaneously on a piano or on a guitar, it composes a harmony. It composes a thing that can compose a harmony at all. Okay, and how we can represent chords? Because in every machine learning program, you need to put the data in some kind of format that computer understands. For a musician, just chord symbol that you have seen just before is understandable because he knows how these chords are constructed. What does the dash mean? What does the other symbols mean? But for a computer, it's not so obvious. The best form of representation is, of course, binary representation, numerical representation, which in end of every data preprocessing is the final form. So what you can see here is my proposition. You can count the notes starting from the C, which is the base of the, I would say, the most common octave, numerically 1 by 1, and light the vectors, light the bit in the vector that are connected with the notes. Very simple, right? Okay, that's not the end. That's only the beginning, because this kind of representation isn't perfect for a computer. It's a binary vector, and how I can change it? The thing that I proposed at the first is components, but we can represent it as a binary form. Well, 0 goes here, 3 goes here, 7 goes here. This is I would say a map that you can put on a keyboard and it will form a chord. Okay, so how to get the data? We know how we can represent the chords in the most simple form, but we need to get a lot of data. Every machine learning program requires a lot of data. And how to get them? I focused on a jazz. Why jazz? Jazz is a music that basically is a root of every genre that we know. Every music that you have on your phones that you're listening going to job has roots in a jazz. Because if we didn't have jazz, blues, probably we'll be listening to minuets or Bach kind of music if it didn't develop like the jazz. So jazz is the roots of Arabic genres. If you look on the Wikipedia, you have a big tree where jazz is in the beginning. Actually, the root of the jazz is the blues. So definitely look at the history of music and how the huge genres, techno, rap, rock, how it evolved and why jazz is the root of all the music that we are listening to. I decided to use jazz because harmony of jazz is one of the most complicated harmony and one of the most beautiful. It gives so much possibilities. It's one of the most complex, and jazz harmony gives you basically everything that you need to write a song. The thing that you see on the right side of the screen is a basic chord representation of a jazz standard. We can see that it's split in lines. Each line consists of 4 measures, and in each measure there are 2, 1, or different number of chords. How to get this data? There is an app called iReal Pro, which contains these representations of a lot of standards. I've gathered from the internet over 2,000 jazz standards, and this is an example of what I have. Title, composer, style, key, and of course the chords. How do they look? This is the raw data that I get from the internet, from forum of iReal Pro. As we can see here, there's a flattened measures, which is a representation of chords. Here are 2 chords. Here also. I just need to parse it to extract these chords, and that's all I need to get the sequences of the jazz songs. They are quite long, and I treated them like a sequences. What I've done next, each chord consists of 2 things: the root and the extension. F major 7. What does it mean? Chords have that property that you can translate them. You know, when a guitarist is playing and a vocalist is singing, and she says, "Hey, you know, can we play a little bit higher because I cannot sing that low." And no problem. And he put a capoduster, put on the fret, and he can play in a higher key. That is because he can play the same chords, transpose it. This is the thing, transposition, and play it in a different key. So chords can be and exist in a 20 different keys. And this is the first thing, the root. There are 20 notes, as I showed you before. 1, 2, 3, 4, 5, 6, 7, 11, but with 0 it's 20. So, 20 possibilities for the root and for the extension. What's the extension? Extensions tell us what kind of chord it is, what emotion it brings. You can play a chord that is happy. You can play sad chord, or a chord that is in the middle part of the Bach, Fuga Bach, and it's very building the stress. So different kind of chords have these symbols. And what does symbols mean? There's a big table that actually runs to the first floor, but I didn't put it all on this slide. And these symbols have their extensions. So if I have C, this will be 0. If I have D, this will be 2, 5, and 8. So I just need to transpose it, like on a guitar. Put all the numbers up by 2, or 3, 4, 5. How much do you need? So okay, we know what does mean the symbol of a chord. So how what we can do with this chord? I find a big analogy between a music and a spoken language. Why this analogy? Because what is a language? Language is a way that we communicate with each other, that we can express ourselves. What is music? Nothing else. We can express ourselves, we can communicate on a more abstract level. And I think that, wow, so if language and music is so similar, and the main idea of it is similar, you can hear it, because it's a sequence. It's a music. For me, language is something like I can hear. I'm a musician. I hear things. And I can hear the language. Spanish is different. Polish is different. English is different. I can hear it. And the same with the jazz songs. With songs in general, in the music. I can hear the differences, how it's changed through the time. So I decided to use these analogies. And how this apply to neural networks, to the machine learning. How many out of you use artificial intelligence every day? Okay, I would say that every person should bring the hand up, because what you have in your pocket, a phone, it uses machine learning all the time, even if it's really, really old, because translation uses machine learning. You want to check how it is in Spanish, you translate it. You don't know where is the sky scanner on a Google map, and you search for the shortest path. You use machine learning with the Google. So we use it quite often. And I decided to use machine learning NLP models to model music, to model harmony. Who knows what it is? Okay, many of you, great. This 3D graph shows words that are placed in this 3D space in some kind of relation. This was a hit using NLP models and a thing called embeddings. When we want to represent something in a different form, as I showed you with the chords, I can represent chord by a symbol or a vector. You can represent a communicate of the language in a different ways. You can tell it, you can write it down, you can encode it somehow, you can translate it, and you can embed it. You can represent it in a multidimensional space. Embedding is a thing that from one thing, let's say this word king, it represents it as a vector in a multidimensional space. Word2Vec is one of the embeddings. Look, this is the input, for example, king, and this is the representation of it. And this is the output. It should be king. So our Word2Vec model represents words as an embedding, and this embedding has properties. These properties can be visible here. And the main property is that the relations between words that are similar to us are visible in space. That's because the method of training of these embeddings are built that way that the similar vectors are represented in a similar way. Sorry, I have to be talking a lot for the whole day. Okay, so since we've been got to this point, I can talk. To understand the concept, we represent the objects in a multidimensional space. So a vector in space, but more than 3D. The 3D is just a simplification, it's a dimensional reduction, but can show us the relationships between each of the points. We represent each of the elements in a multidimensional space. The most basic embedding for words is Word2Vec. You see it in a name, word to a vector. It uses a neural network, one layer neural network to create the embedding. Fast text, both of them are implemented perfectly in GenSim. Our extension of Word2Vec implemented by Facebook that uses n-grams. N-grams is parts of the word with a certain length. So from fast text, I get fast STTE text. And from chord, I get something like this. As you can see, it makes sense, for me at least, because part of the chord also tells much about what it means. This is the second one. Okay, experiments. So I trained the embeddings on a multi-hot representation on a Word2Vec and a fast text. And the basic test that it used to test an embedding is the following. To test out embedding, it's a custom test that consists of set of pairs of chords. So as in the example here, I have a word king, queen, And I expect it to be in some kind of relation, and man and woman should be in the same kind of relation, which is codependent. And I've created a set of tests to test the chords. For example, root change. I have the same extension for every chord, and I change the root by the same amount, by 2 semitones, CD and FG. Chord type change. I have the same root, and I change the extension. This relation and this is the same, and I expect my embedding to show somehow this relation. This is the result. Multi-hot has accuracy of 0.6%, so it's very, very low. Dorobek 3.7 and fasttext 11.8. But these are just the numbers. We know that the fasttext may be the best, but what we can see actually from these results. 251 progression, one of the most common progression in songs, in a jazz. It's simplified version. It's also very popular in pop music. These lines, I wrote it in Python, sorry, it's so bad, but it's only to show how these relations are in this embedding. Multi-hot, they didn't see much relation here. In our Dorobek, all these chords are connected in one straight line. And fasttext, all these 3 chords are in the same place. What does it mean? That means that they exist in a similar context. They're close to each other because they exist in a same places in many, many songs. Circle of fifths. It's a music structure that connects the most similar chords, the most similar keys. Complete mass from multi-hot embedding. With fasttext, it's a little bit better, but look what happens in our Dorobek. It's a circle, and what is more, it's in a perfect order. So when I saw it the first time, I was like, oh, it's not possible. I have to double check it. Oh my god, it's really in the same order as in the music circle. Why this? Because these chords represent the keys, musical keys. This is F major, like C mixolydian, G mixolydian, D mixolydian. And the difference between these two is only one sign. Difference between these two is also one sign. Difference between this and this is 6. So it's the biggest. Okay, so that's the result of my embedding. And I've decided to use this representation that somehow shows a similarities between chords. Because when I show you C7 and G7, okay, maybe C looks like a G, but it makes no sense to a computer. So I've decided to use this embedding, which shows similarities. In a space, this vector is close to this vector and far from this. And as a musician, I know this chord is close to each other and far from this one. So when I have this special representation, I can use it in machine learning. Okay, LSTM. What it is? Who knows? Okay, this is a neural network, recurrent neural network that has some special mechanism inside that I will tell about. Recurrent neural networks, they work perfectly with sequences data. And LSTM is even better because it can look way to the back and remember what was at the beginning of the sequence and use it to generate new sequences. My problem is the regression. I want to create a numerical vector with continuous values from 0 to 1. So I decided to use LSTM and my embedded chords. This is the architecture of my network. Quite simple. Input is the size of embedding, and output also the size of embedding. I've input 3 chords and output 1. So as in the beginning, I had 3 chords, 1, 2, 3, and the 4th is the result of my generation. I've gathered the data to the sequences of 3 and a 4th And this is the result of generation. We have these three chords. It's sampled from training set, from test set, sorry. This is the chord that existed in this, after this sequence, and this is the proposition of the neural network. Of course, neural network doesn't produce the exact point. Imagine we have a 3D space. We have chords here, 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 here. And the production of neural network is here. So it's not perfect, this chord, but I use the most similar one. I get this chord, this point, and this point represents this chord. So that's the result of the generation. For non-musicians, so not much, and for musician, as I can see it, it's not the best, but definitely there is some kind of relation to these chords, because these are flats. I can simplify my process of thinking. These are flats. There are a lot of flats here, here and here. This is E. This is one step below, and this is 1/4 higher. So I think this is some kind of thinking that a musician may use. Okay, this is the generated sound. I put this sequence at the beginning, these 4 chords, and then this is generated. They used 3 chords actually. Put this 3, it generated this. I put 1, 2, 3, this 3, and it generated this, and so on, so on, so on. So I generated a song. Okay, do you want to listen? Yeah. Me too. And AI. 1, 2, 3. It wasn't AI. Okay, what we can see here. This song is quite easy. A lot of chords repeated. A. Actually, there are 4 kind of chords. This A is a dominant to the A. We can hear it. Okay, we won't hear it. But this is a dominant. This is the most basic progression. 5-1. 5-1. This is also a dominant progression because it's a backdoor dominant. It's not so common, especially in pop, but when I saw it, wow, that's a clever idea to use the backdoor dominant in this moment. This chord, I would completely don't use it. It's really how you can think of it to use it. But actually, when I listen to it, maybe that's an idea. Maybe I wasn't thinking of it, but that's the way. Use the completely different chord, and that's what the AI is used for. To bring you ideas that are, or at the first look, completely out of mind. I wouldn't use it. But AI told me that this is some kind of relations. Try it. And I think that's a really good result. Okay, conclusions. What I can say about my work. This is the part of my master thesis. And definitely it's not done. It lacks of analysis. It lacks of building a better model and test it out. But the results that I have bring me a motivation to try it out because they are really, it's a small blink that it's working. It may be working because there are embedding that are in relations. These generated chords were okay and completely out of line. So somehow I need to fix it up. And there are a lot of things to do, but I think that's a really good way to use word embedding to music to connect these words. Spoken words that are occupied by Google, Facebook. Everyone wants to make automatic translation. But not everyone wants to AI generate music. Actually, this branch is very limited and not many people are doing it because it doesn't bring money. But it brings results that musicians may use and learn from AI. So this is my conclusions. If you want to follow my work, I made a project similar to this when I've used DC GANs, networks that works with images, music. So the same analogy, language to music, images, and I've used a DC GAN algorithm proposed by Ian Goodfellow to generate images. I've used it to generate music represented in an image form. Look, this is a music. This is a piano roll. This is like in a Guitar Hero. You play it from here to here. There are 64 of it, and this is how it evolves. You can also listen to it if you want. Okay. It gives really different examples. This one song that we could, okay, it's not trained, so it's not working, but it consists of 2 chords. And the following song that you can hear in a second consists of a melodic line. So as you can see, using images to generate music, I've decided to give it free hand. Do whatever you want. I didn't put any limitations because many of works made with music, even by Google, are very limited. And I wanted to I'm inspired by jazz. When you have free, you can do whatever you want. And I've decided to give it a free hand, but not limit it, and see what it will result. And this project shows me that images networks, CNN networks, work very well with music, but you need to fix one thing, because when you have image and you split it and you turn it, rotate it, it's actually quite okay. Okay, you are still people, okay, people there, great. But if you do this with music, it makes no sense, because in images, this is a distance, and this is a distance. And in music, this is a frequency, and this is a time. So it's different. And you cannot use square filters in a convolutional layers. You have to use other types of filters, but it's a completely different story. Okay. Do you have any questions before I thank you for the presentation?
Please let me know so everyone can hear you.
So thank you for the presentation. I would like to ask you, the diagram when you follow the circle. When you have seen the circle, how you decided that you are in the right direction, projection?
Okay, very good question. I skipped it, but as I said, my embedding was size of 64. So 64 dimensions. How you can even imagine it? It's hard to imagine 4 dimensions. I use a dimensional reduction technique called TESNI. PCA is also a good choice, which chooses the most important dimension. So if in my 4 dimension, time, like time is a very common used example of 4 dimension. 3 dimension is me standing here. 4 dimension is me walking here through the time. So basically here or there. And as you can see, if we reduce time, put it out, it's either here or here. So we can use the most important dimensions. And I've done the same. If you go back to this slide, I reduced the dimension of my points. So I choose 2 the most important dimensions. And only these 2, this relation occurs. So imagine what happens in a multi-dimension, in like 64 dimension. It's also a circle, multi-dimensional sphere. It's even better. This is a reduction, and maybe this will be better, and this in multi-dimensions. I've made a reduction. It's a lot of noise in this, but even after reduction and putting this noise, this is visible, and this means a lot, at least for me. Okay, I hope that I explained it, the reduction technique to show this.
Any other questions?
Yeah.
Thanks for the presentation. So I did not fully understand how you train the embedding. Like, what did you feed into the embedding?
Okay. Training and embedding is telling him that he should consider 2 words as a singular one. I can explain it on a words example. You have word I and you have word M. They exist in a similar context. And these words should be similar in an embedding. And maybe this idea, quite easy, shows a big result. And what do? You get this pair, and you expect a neural network
single words.
I've put a pairs of. I've used a skip ground implementation because there are two ways. You get either continuous back of words or skip ground. Skip ground, the thing that I use, I have a sequence of chords. I take chord from the middle of it. This is my first thing. This is my input to the neural network, and my output is this, the next chord, and the second chord from this, and the previous one. They all exist in a context. Continuous back of words is a different approach when you put this as an output and this as an input. Okay.
Well, please give a round of applause to Mateus for his amazing talk.
There was one question. Yeah.
Yeah, you said you consider.
This one is.
Given that you consider music as a language, have you considered using transformers so maybe you can have like longer sequences of instead of the following to the other? Have you considered using bird transformers or something like that, where you can gather the structure of the whole composition?
Yeah, it's in the to be done column. Yeah, definitely this is a good idea. Do you have any other things that I can use to deal with changing various length of the input? So imagine that I have song and I have one chord that I want to start with, or a random noise, because if I put the three chords right now, it will generate the same thing, my LSTM. What can I do to make it better, like to deal with the varying length of the sequence?
I don't know about the specific mapping, but I would certainly look into the transformers because of the amount of context that you can put into it. It's just a suggestion because I know it works in order to generate language, so I was thinking maybe it would be useful for music.
Yeah, definitely. Thank you for that. That's a good point.
Cool. Please, another round of applause.